Okay. Right. Yeah. So I don't think I need to explain what Lean is here. What'll be relevant for this talk is that Lean is an ITP. Probably all heard of it. A lot of people like it. It's based on dependent type theory, or more specifically, an extension of Martin-Liff type theory called the calculus of inductive constructions. So in 2019, I worked out sort of the main properties of Lean type theory for my master's thesis, and it's been 5 years since then. Well, a bit 6 years now, and we have a new Lean version which has made some kernel changes. And Lean has had a few very short-lived minor soundness bugs. So I've sort of been working on a project to formalize the kernel. And so the basic one-sentence summary, the takeaway is it's Metarock, but for Lean. So Lean is about 80% written in Lean. That includes the parser, the elaborator, the tactic language, the metaprogramming framework, even the LSP server. The exceptions to this are the runtime that's written in C. It's very small. The interpreter, you could argue that this is for performance reasons, and some legacy code, and the kernel. And I think that of all of these pieces, one of them is both mathematically interesting and soundness critical. So we should probably do something about that. So the basic project goals of Lean4Lean are to make a Lean kernel which is complete for everything that the original can handle, and is actually competitive with the original so that it can be seriously considered as a replacement for the Lean kernel. The second part of this is to write down the type theory of Lean, but formally this time in Lean itself, not just on paper, and prove the sort of structural properties about the type system. And the third part is to prove the correctness of the implementation, this implementation of the kernel, with respect to the specification in the second part.
Regular question. What's the interpreter and why is it not possible?
So the interpreter, so Lean has a couple ways of being able to run code. The interpreter is what you would get if you're running your tactics, if you use hash eval in order to evaluate things. It's the sort of untrusted computational approach. And it's an interpreter. It's separate from just like beta reduction, which is sort of closer to what the kernel is doing. This is more of a compilation kind of approach. And so this is sort of a list of how the progress on the various goals. And so the structural properties of the type system are in progress. And as of recently, the correctness of the implementation has also sort of broke ground on that one. All right, so the Lean4Lean kernel is basically a carbon copy of the C++ code. It does all the same fancy tricks as the original and all of the same stupid tricks as the original. So it uses union find data structure for caching. It's got pointer equality testing. It's got bidirectional type checking. It uses identical definitional equality heuristics. It has the eta for structures. It has nested inductive types. It has naive implementation of substitution and reduction, just like the original. So it's actually, I mean, this is on purpose. It makes it suitable for sort of differential fuzzing. Like I can see, when do they ever change, if one has a behavior, the other one also has the same behavior. I can count up exactly how many times is a definition reduced, and it's the same, that kind of thing. And it uses Lean's own expert type. So a few algorithms are implemented in Lean. So Lean kernel is written in C++, but it calls out to Lean for a lot of things. In particular, the expert type is implemented in Lean, and C++ will use the Lean's implementation of that. And so some algorithms are written in Lean, and when possible, I try to reuse those algorithms. All right, so here's just some stats on running the Lean kernel on some stuff. And so the performance is about 30% worse than the original. This is quite good. I think it could be better, but this is quite good. Lean itself took hits of a similar order of magnitude when it moved the elaborator out of C++. In Lean 3, most of Lean was written in C++. In Lean 4, almost all moved to Lean. So this was worth it at the time for the improved extensibility and development features, and it has since clawed back all of that performance and more by being able to do better algorithms that were difficult to get right in C++. And so I want to basically do the same thing with the kernel. I think there's a lot of things that can be done to make it more efficient. And currently people are just afraid of making changes for the chance that it'll introduce a bug. And this is a way of, if we prove it correct, then we'll feel much more confident about being able to make changes without introducing bugs. So this is my recall DTT slide. So I think I can definitely assume that everyone here either knows or pretends to know what's on this slide. The only thing that I'm going to bring up is the only thing that feels maybe a little bit unfamiliar here is that Lean uses this Imax function for calculating the universe level of a pi. So this is an impredicative universe of propositions, and that has this hierarchy of universes, and it uses algebraic universe. So it has this Imax function, which this is how you model it, but it basically does the algebraic theory of Imax and max expressions. It has definitional proof of relevance. It does not have universe cumulativity. It has index mutual and nested inductive types, and it has an eta reduction rule for lambdas, structures, inductive types. It has iota for inductive types. It has eta for structures specifically. So we want to, it also has proof of relevance, as I mentioned. So we want to treat all proofs of a proposition as the same. That means that equality has at most one proof. And to prevent inconsistency, this means that some inductive types can't eliminate to a large universe. So if you define existence, then this will have a recursor that only eliminates into U0, that is to say prop. Whereas if you define, there are some specific inductive types, for example, the accessibility predicate or equality, which do eliminate to all universes, and this is called subsingleton elimination. So there are also 3 actual axioms, as in they're declared with the axiom keyword and sort of layered on top of this base theory. Those are propositional extensionality, quotient types, and the axiom of choice. And so this project is basically formalizing the meta theory of this entire thing, including the 3 axioms. So there is a sort of obvious model of dependent type theory in Zermelo-Fraenkel set theory, where we treat types as sets and the elements as the elements. I like this. This means that I can understand what this type theory is. I'm not a big fan of where it's just syntax and syntax begets more syntax. So you have an interpretation function, which translates every expression in a context into an element parameterized over another set. And so the model of propositions is just a 2-element set. And the representation of universes is with Grothendieck universes. Okay. So as a consequence of having such a model, you have a consistency result, right? So if you have a proof of if you have a typing relation, then there's a corresponding elementhood relation. So if this was a proof of false, then this would be an element of the empty set. And so this says there's no proof of false under some, assuming that you have what's necessary in order to set up this model in the first place. So this is a relative consistency. So Lean is consistent with this theory, ZFC, with the statement for each n that there are n inaccessibles. So this is a sort of infinite family of axioms. And you can do it the other way around. So you can construct a model of ZFC with n universes in Lean. Okay. So the type judgment has there's a sort of combination of things that you can put together, which I won't explain more here, which show the undecidability of the typing judgment. This is sort of an unusual situation which people don't run into, but I should mention it. So, and in particular, Lean resolves this sort of by not actually doing the full the abstract typing judgment that is undecidable. Instead, it does some under approximation of that, which trades decidability for for loss of transitivity and subject reduction. So when people talk about it not being transitive, it sort of depends on what you mean, whether you mean this sort of relation or like this sort of idealized completion. And in Lean4Lean, we're mostly going to be concerning ourselves with the abstract judgment. So the idea is if we can prove that the typing relation is consistent, even if we do this completion, then even if you're only doing some subset of that, it's still fine. So the biggest theorem in my master's thesis was unique typing. And so while I started formalizing this theorem and I found a gap in the proof, I still believe that these theorems are true, and there's an alternative path to the proof of soundness. So basically, the statement here is that if you have a term that has two types, alpha and beta, then those types are definitionally equal. And this is proven mutually with these three things here. So this is basically injectivity of type constructors. These are very sort of important structural properties of the type system, and the kernel does depend on them quite a bit. So here's the way that the proof basically works. So it's using the Church-Rosser theorem. So there's a Church-Rosser theorem for lambda calculus. Here there's a Church-Rosser theorem that gives you something close. So the idea is you have E1 and E2, which are definitionally equal, and then you're trying to figure out sort of how you understand why they're definitionally equal by having a reduction system. And so I introduced this reduction, the squiggle kappa, which reduces it such that, well, ideally they would come together, but they don't quite come together. Instead, they sort of almost come together, and you have this relation, this equals P, which is equivalence up to differing at proofs. So because of proof irrelevance, you can have these, like, these don't have any meaningful reduction theory. So you just sort of stop there. But this is still good enough in order to get the injectivity of type constructors that we want. I think I want to skip this. So the original proof uses stratification of the typing judgment for this induction order, but that turned out not to work because it's not closed under substitution. The sort of Church-Rosser part of this proof seems okay, but we need a better induction measure. And so I've basically decided to set this aside and sorry it for now, but the Lean kernel really does depend on this. And so this is sort of my request for type theorists wanted. I don't think that this is too hard, but I'm working on a lot of things, and so if I can find someone to work on this problem, that would be great. All right, so let me tell you a little bit about verifying the kernel now. So Lean does not just implement the type theory as I sort of wrote it there. It has a laundry list of optimizations over the obvious definition in almost every single function. So as a result, verification is quite complicated. So one of the ways that I sort of try to simplify from the original expr type is to introduce this v-expr that looks very similar to what I showed at the beginning, but expr has a bunch of extra stuff in it. So expr, for one thing, uses locally nameless representation. v-expr is doing pure Debrun. Expr has a bunch of additional primitives, so it has natural number and string literals, so that like you can have 37 just stored as an actual natural number, and it will actually compute with those as well. So if you have 37 plus 22, the Lean kernel will recognize you're applying the function nat.add, and then it will, instead of unfolding the definition of nat.add, which does a computation in unary, it will it'll run GMP in order to evaluate these functions. And it also has meta variables and free variables, which mostly don't matter, but the free variables are handled in the kernel, and primitive projections, which actually cause a lot of problems. The translation from expr to v-expr can mostly be done as just a function, but when it comes to primitive projections, you run into trouble because primitive projections are morally supposed to expand to an application of the recursor on the inductive type, because the structure in Lean is an inductive type with one constructor. And the way that you define these primitive projections is just by applying the recursor and then taking out one of the arguments. But in order to actually do that, you need to know the type. So the primitive projection just has the expression, and then it says it's taking like a .1 or something. It takes one of the fields. And in order to understand what that means, you have to do the typing. So this becomes a typed translation, and that makes it not unique, and that causes a lot of issues. Oh yeah, and expr caches metadata, like, do I have a free variable inside every sub-expression? That's foreshadow. So there's been some recent progress on the program verification part of this. So I'm sort of just stating these in a one-sided or logic kind of style. So on the right, I have a post condition, that's Q. And on the left, you would usually have like a P precondition, but instead of that, I just have like you're equal to some initial state. And so here's an example theorem. This is sort of the main theorem, and this is one piece of a sort of giant induction over all of the functions. So I can sort of assume this, but I also have to prove it at the end, and that part hasn't been done yet. But so this statement here, this is stating something about the infer type function. Infer type takes two arguments. The first argument is an expression that we're trying to type check, and the second argument is a Boolean value which says, are we type checking it, or do we already know that it's well formed and we just want to know what the type is? And so this is the case where we've said infer only, which is the name of this, is false. So we're type checking it. And so the idea is you pass in the expression and then you get a type back. And if this is successful, then the expression is well formed, and this E prime here is the V. So this is an expert and this is a V expert. So this is the sort of the abstracted version of it. So that this has a nice abstraction. The tie also has it's well formed, and then the expression has the type of the type. All right, so this verification is already paying dividends. So last week I was working on proving this has bound var correct, and this does some thing with bit fields, which worked out all right. But the metadata calculates some depths of bound variables, and so this sort of can overflow. It did check for overflow, but it actually made the problem worse when it panics. And so this turns out to be a soundness bug. And so I submitted a PR that fixes this, and we'll see what happens in the next version. So you can use Lean4Lean as a replacement for Lean's kernel today. The formalization is under active development, and there's still some more mathematics to be done. But there's a half a dozen people working on Metarock, and there's just yours truly working on Lean4Lean. So if you identify as a type theorist, then come help me out. Thanks.